Yeah, sir.
Oh,
You got it.
all right. So we're going to do the differential amplifier. The circuit you will build will look something like this. It will have an RC, and there will be a transistor here, call it Q1, and its output will be VC1, and there will be another, let's call it as V small capital C1 for now. And there will be an identical transistor here, and I'll get to the circuit later. Let me first discuss the idealized circuit and then the circuit that you will build. And here there will be a current source, and it's given to you that, let's call this as V1 and V2. It's given to you that in the steady state, this current, each of these should be 1 milliamp. Now these are transistors, they're not MOSFETs, so there will be some current going into the base. But normally we can neglect that current because it is much, much smaller than the collector current. Do you remember that? Roughly what factor is the collector current bigger than the base current by? Give me a number. 100, 150, something like that. So in the big picture, we can just assume that the collector current and the emitter currents are equal because the base current is so tiny that it probably makes no difference. It makes a difference for something called a power transistor, but these are not power transistors. Okay? So later on, if you do power electronics, your betas will be closer to 25, but here they will be closer to 150. So you can ignore that. So if that current and that current have to be 1 milliamp each, what is this current going to be? 3, 4, 5, 6, 7, 8, 20, 100, 2 milliamps. Where 1 milliamp comes down this way, 1 milliamp comes down this way. This is 2 milliamps. Of course, some little bit of current goes in this way too, but that is negligible. Or we can assume that it's 100 times smaller, 150 times smaller than that. So we can, for the design of our circuit, we can neglect it. Now, if you had a circuit like this, the way this differential amplifier works is that it, let us say that these two voltages are equal, and we actually take the difference, the output voltage is measured between the plus and the minus terminals Vout. And suppose I apply the same voltage here. Let's call this voltage as VCM. It will be clear what VCM means in a minute. But let us say we apply a voltage VCM here. Same voltage on both sides. Okay? Now obviously the currents will change in both the circuits. But will the current here be equal to the current here? Will, for example, IC1 be equal to IC2? Will IC1 be equal to IC2 if I apply equal voltages VCM to both the bases? What's your gut feeling?
It should be.
Yeah. Why is it your gut feeling?
Is it the same?
Everything's the same on both sides.
Everything is the same on both sides. So by symmetry, one would expect that these are the same. And therefore, what is the difference between VC1 minus VC2? 0. So applying the same voltage, or what we call a common mode voltage, to both the gates, both the bases. Got to flip over to a bipolar talk now. Applying the same voltage to the base, both bases will not result in any output voltage differentially taken between the two outputs here. Right? So this thing does not amplify so-called common mode voltages. Have you heard of common mode voltage before? No. All right. Now, by the way, in this case, your intuition is correct, because if you expose both sides of the op-amp to exactly the same excitation, which is VCM and VCM, we expect identical responses in both. If there are identical currents flowing in both, this voltage and this voltage are of course identical, and therefore the difference between them is 0, and you would expect no change. Sometimes your intuition is not true, by the way. What if I take a coin like this, and I do an ideal toss? So what should the outcome be? Somewhere between heads and tails, exactly the average of heads and tails, right? Average of what? Both sides are exactly identical. But it came out heads, right? That's when your intuition failed, because if you say it should be the average of heads and tails, then it would be not correct. I'm reading a book on quantum mechanics right now, just general purpose reading, and a lot of interesting questions like this in there. It's a popular book, it's not high math or anything like that. Has anybody heard the paradox of Schrodinger's cat? Yeah. Is it dead or alive inside the box? That kind of thing. So anyway, we won't get into that. This is simple, this is electronics. Okay. Alright, so this is 2 milliamps. So this is, okay, so this will not amplify, ideally this will not amplify any common mode signal. The only time it will amplify a common mode signal, common mode means the same voltage applied to both, is if these RCs are different. Okay, if they are slightly different. Will those two RCs be different if you design this circuit yourself for this, with the same RCs? Can they ever be different? What's your opinion on this?
Just like
Why?
tolerance.
Yes, as you can see, somebody's already written that here. The gold means 5% and silver means 10%. So depending on your resistor, if it's got a gold band at the end, when you say 10K, it may be off by plus minus 5%. Right? So it's possible that both these are different. And so the common mode gain will only change if the resistance are different. Now in this lab, they've asked you to calculate the common mode gain, but they haven't told you how much uncertainty to expect in RC. So if you want a theoretical answer for this, you'll have to actually measure the RCs. But for this lab, I'm not expecting you to give a theoretical answer. We're just asking you to measure the common mode gain and report it. But if you want to do a little bit more for bonus marks, you can actually calculate it. We'll see how to calculate it in a minute. But now, so we can say that in the general case, the voltage applied here will be a common mode voltage and a difference mode voltage. Let's call it VID over 2 is the difference mode voltage. And then this is the common mode voltage. This is not the same thing as, could be capital CM also. And so here then we have a difference mode voltage and a common mode voltage. Now this is not necessarily a bias voltage. It's not necessarily a bias voltage. It could be any two voltages that are identical. These two identical voltages together will have no effect on the circuit. The only thing that should have an effect on the circuit is these. Okay? And we say that the difference mode voltage VD is equal to V1 minus V2, and the common mode voltage is equal to V1 plus V2 over 2 at the base. This is V1, this is V2. So V1 plus V2 is the common mode voltage. So in fact, if I've connected the circuit like this, you can clearly see that if I add these two voltages and take the average, I'll get VCM plus VID over 2 and VCM, and the polarities are like this. They are opposite polarities. You can see if I add them up, the plus VID by 2 and the minus VID over 2 cancel each other out. I get 2 VCM divided by VC2, which is giving me VCM. Okay? So that's common mode voltage. It's very easy to calculate. And indeed, if I were not having any difference mode voltage, then the two common mode voltages applied equally to both gates would have no effect on the circuit. So the only thing that would have effect on the circuit is VID and VID. Alright, so now let us draw the small signal equivalent of this, keeping in mind that the common mode voltage has no effect on the circuit. So then we will get something like this. You'll see RC. This is the small signal. RC. I'm going to ground this because I feel like it. Why am I grounding this? Because yes, that's the right answer. It's not just because I feel like it, but this is a battery here, VCC now. We don't say VDD for bipolar. This is VCC for the signal, it's a short circuit, so I'll short circuit it. And then I'll draw the equivalent circuit of this. What equivalent circuit do I use here? I'm not sure whether you came across this circuit or not, but this is, I'm sure you did. This is alpha times IE, alpha times IE. This is the base. This is RE, which is, well, we'll write its value in a minute. This is RE, they're connected together. What about this ideal current source? What's its small signal equivalent? This is exactly 2 milliamps. So what's it? How do I represent this in a small signal model? Yeah?
It's open, sir.
It's open circuit because you can't make any change to it. So you can't incrementally change the current in that circuit. So it's an open circuit. Just like the DC source is a short circuit, the DC current is an open circuit. So I leave it open circuited like this. And I will connect my voltage VIE here. Okay? Because there'll be, if I go around in this circuit, I ignore the VCM because it has no effect on my circuit. Then I have plus VID here, minus VID here. So connected between these 2 points is VID minus VID over 2, which is VID. So I very interestingly get this equivalent circuit, and this is my point VC1 and VC2, and you can clearly see from this circuit that your if I go in this circuit, go around a loop like this, what is the current here? IE. What is the current here? Same current goes IE like this, which is equal to, so IE1 is equal to IE, and let's say IE1, and IE2 is equal to minus IE1. The same current has to flow, there's no other place. So IE1 here plus IE2 must add up to 0 because there's no place to go, which means IE2 which is equal to minus IE1. And so if I go around Kirchhoff's voltage law in this loop, KVL, I will get VID minus REIE1 minus REIE1, REIE1 this way, REIE1 this way, is equal to 0, and that will give me IE1 is equal to VID divided by 2RE. So you can see that this is REIE1 plus REIE1 gives you 2 REIE1. That you divide VID by that and you get IE1. So you got the expression for the current there. And so IE2 is the same as minus VID over 2RE because it's there. Now do you know what this RE is? Do you know what it represents? This is the T model of the this is the T model of the transistor. You can also write the other model, which is this kind of thing. R pi and beta IB and IC, and this is called the pi model of the transistor. I'm choosing not to use this one, and this is the corresponding T model. Did you do T models in your previous course? So that's just the T model. And if you really wanted to know what this, alpha is a parameter of the transistor. It's very, very close to 1 because collector current and emitter current are practically the same if the transistor is in the active region because the base current is so tiny. So alpha is a number very near 1, and it's related to the manufacturing process of the transistor. But just for information, we are not going to use the pi model, we are going to use the T model. And if I use the T model, just for your information, the value of this RE is actually VT divided by IB, which is a bias current, or you can even write it as beta VT over IC, because IC and IB are related by the factor beta, which is the beta of the transistor. Now what does VT mean?
Thermal voltage.
threshold voltage of the MOSFET. But there's no MOSFET here, so it cannot mean threshold voltage of the MOSFET. This VT is the thermal voltage. Sorry, it's not the threshold voltage of the MOSFET because there's no MOSFET here. So it's a thermal voltage. And its magnitude is K, where K is the Boltzmann constant, multiplied by the absolute in Kelvin, divided by the electronic charge, which is 1.6 times 10 to the minus 19 coulombs. And if you measure this at roughly room temperature of 27 degrees or so, this comes out to be approximately equal to 25. What are the units?
Millivolts.
Kilovolts? Megavolts. Or millivolts. So it's roughly 25 millivolts at room temperature. So this is 25 millivolts. IB is the bias current IB, or IC is the bias current IB. What is IC here, by the way, in our case? 1. Because there's 2 milliamps in total in both the transistors, so IC is 1. So it's basically 25 millivolts divided by 1K multiplied by beta would be your value of RE. Alright, is this correct? Yes, VC.
Maybe
VT over IC.
it's VT
So-
over IC.
Sorry?
So maybe RE is equal to VT over IC or IB.
VT over IB is R. Oh, sorry.
VT
I'm
over
sorry.
IC.
It's VT over IE, which is approximately equal to VT over IC. My mistake. That was for RI I was looking at. That's something else. Okay, this is VT over IE, not IB. And that is basically almost the same as VT over IC because IC is equal to almost alpha IE, which is practically the same thing. So in fact, in this case, you can easily say that RT in our case will be approximately 25 millivolts divided by 1K, 1 milliamp. So approximately 25 milliohms, 25 ohms in our case. Approximately. It will depend, go up and down on temperature, but essentially more or less that. All right? So, now this is our IE, and therefore VC1 will be equal to minus IE1 times RC, because this is 0, this is IC, so, which is the same as IE. So, minus IC1 times RC, which is approximately equal to, which is exactly equal to alpha IE1 times RC, and so that will be equal to minus alpha over 2RE times RC, and I can say that this is approximately equal to, I'll write this as small RE by the way, because I think that's what we call it there, not capital R. So, this is IE that I put in there, alpha because IC is alpha IE, and so this I can write approximately as minus RC over 2RE. Because RE, alpha is approximately 1. So this is the single-sided gain of my op-amp. The single-sided gain of my op-amp. So what is the, what about VC2 over, VC2 over, divided by, I'm sure there should have been a base over it. RE is VT over IE. Okay. 2RE and VC2 will be equal to exactly the same. It will be plus RC over 2RE. Because the current IC here is equal to minus of the current IC here, because it's this, both emitters have the same current, but they're opposite in direction, so the ICs will also be opposite in direction. You'll simply get a minus sign there. And that will give me my differential gain VO, which is the output, which will be VC1 minus VC2. Will simply be minus RC divided by RE times VI D. On my difference mode gain, AD, let us call it, difference mode gain, will be equal to minus RC over R. because I divide V0 divided by VIT, which gives me the difference. Now, one of the things that the book says, or the sheet here says, that you don't want this gain depending on RE, because this RE could change with temperature. Let's change with temperature. All right. It could also change sometimes if you have some mismatch between the transistor characteristics. So what we do is we just add a little bit of external resistance to it on purpose. And I'm looking for my chalk. So what we would do then is we would purposely add here some external resistance, call it capital RE and capital RE. Okay? Nothing really changes except that in this formula, instead of the gain being just RE, which is the internal resistance of the emitter, we add to it an external resistance RE. And that's nothing. I mean, obviously you can see the math is the same. So this would become just simply RE. Okay, so then now we would have an external resistance. By adding this external resistance, you minimize the variations in this RE. For example, if RE changes with temperature, because you have a bigger external resistance connected to it, right, you will find that your gain will not vary much. In fact, if you choose this RE to be much bigger than this RE, then you can ignore the smaller RE and say that your gain is RC over RE. All right? And that makes your circuit independent of the characteristic of the transistor. Remember, in electronics, we get very sloppy components whose gains can vary, whose performance can vary, and we yet make excellent circuits that give predictable behavior. And by putting an external resistance yourself, you minimize the variation here. So now if this is 25 volts, this is approximately 25 ohms, we use a resistance much bigger than 25 ohms. What's a resistor much bigger than 25 ohms? What about a billion K? Well, of course you have to use your judgment how big you want it, right? Because you want a gain of RC over RE to be, as your book says, you want a gain, in your case, in your design, you want a gain of, what is the number here? Can somebody read from the sheet?
25 to 37.
25 to 27. So you want this approximately RC over RE. If you ignore the small RE, you can add 25 millivolts to it if you want at room temperature, but we don't even know what the room temperature is in this room. So we just have to guess it. So we don't really know what our RE is going to be, but we want to minimize the effect in the variation of RE, so we'll just use the external gain. So we want this to be equal to 25 to 27, something in that range. That allows us to choose the ratio of RC over RE. All right? Okay. So far so good, so you can now select the, but that's the double sided, yeah, that's the double sided. I think it's double sided or single sided? It's at 25. Anyway, you can figure it out. Single sided game of 25?
It doesn't say here, but
Oh no, you measure that. Oh no, it says differential gain of 22 to 27, right? So you want the difference. Differential gain means that, because we said that this is the differential gain. So you want that number to be 27, so RC divided by RE should be 27. All right? So far so clear? This is more or less the problem. But now, look at this circuit here. We had a 2 milliamp current source. How the heck do we get a 2 milliamp current source? In fact, the paper says don't use a 2 milliamp current. So how do you make a current source?
Voltage and resistance.
Sorry?
Voltage and resistance.
Correct. That is a crude and sloppy and very effective way of making a current source. Okay. So, you know, a current source, what is the resistance of a current source? Large, right? So if I just take a voltage, Can I erase this all here now? Okay. So, now let us try to build that current source. And we can do it simply like this. So, we have a transistor like this. And what we will do is we'll just put a large resistance here. Call it R capital E capital E. And this voltage is minus 10 volts, I believe, because that's given to you. And then we have RC and RC, identical, and they are connected here to plus 10 volts. I think that is also given to you. Right? And let us keep, now we have to bias this circuit. We have to bias this circuit. So let us not apply any signal. Let's just apply a bias value. And that bias could be 0 in the absence of any differential signal. So if I apply 0 bias here, what will the voltage be at the emitter here? Guess, give me a number.
-0.7.
Yeah, it will be one voltage, one base emitter junction drop. So this will be approximately minus 0.7 volts. Some people might say minus 6, 5. Who really cares? But it's about minus 0.7. Whether you come from that side, it's still minus 0.7 because they're both base emitter junctions. So if I apply no signal, this signal will be minus 0.7. So here is minus 0.7, here is minus 10. And I want this current to be 2 milliamperes. Does that give you a value for RE? If this is minus 0.7, this is minus 10, does that give you a value for REE? In fact, how much would it be? I will let you figure it out. It's minus 0.7 here, minus 10 there, RE, and I want 2 milliamperes. It's called Ohm's law, you should be able to figure it out. All right? Since I'm not going to do everything for you. So you can figure it out. And that really, if the RE is big enough, this voltage is always going to be close to minus 0.7 without any bias, right? And it should not have any effect. Now it will have effect on the common mode. Suppose I apply a common mode voltage here, VCM, and this voltage will go up. It won't be minus 0.7, it will be VCM minus 0.7. And so it will change. But if RE is large enough, that change will be very small. Okay? Because that change will be, and now with the VCM, it will be VCM minus 0.7 minus plus minus minus 10 divided by REE. This number minus 0.7 divided by 10 is already, we know. We already know that this number is 2 milliamps. We already know that number is 2 milliamps because we designed it for that. So this, if RE is very large, the effect of VCM will be less. And of course, if it's an ideal current source, RE is infinity, and common mode has no effect on our circuit. But in reality, the common mode will start to affect this circuit if we have this instead of a current source, as you're going to do in the lab. Okay, but this is our circuit. But right now we are digressing a bit. We are still biasing this circuit. And when we want to bias this circuit, we want 2 milliamps to flow here, we get RE, that's it. Now what about RC? What should RC be?
Should be based on the ratio, right?
Well, yes, but what voltage would you like here in the steady state? All right. This voltage here, when you have no signal applied, let's ignore the problem. Let's assume there's no common mode signal. So if there's no signal applied, then this voltage is minus 0.7. And this transistor can operate between cutoff and saturation. When it's cut off, the voltage here is 10 volts. Correct? There's no current flowing, so output voltage is 10 volts. When it is, this transistor is saturated, what will that voltage be?
2 volts.
Why 2?
Oh, sorry, 0.2.
Roughly
9.8.
minus 0.5 maybe.
Yeah.
about 0.2 volts across here.
Yeah, sorry.
So it will be probably instead of minus. Keeper never really does that in a penalty shot because in a soccer game there is no time to react. So you just have to guess that the penalty shot is going that way and already move over here and wait. If it goes there, you quite often see, right? You quite often the score dives like this and the ball goes in that corner. You wonder what a stupid guy. But what he's doing is anticipating, because if he really stands in the middle, there's no time to react. But in a transistor circuit, things are different. You want to go up and down, so you stand in the middle, right? So the analogies are not always perfect. So we should have it biased at somewhere around 5 volts. Your requirement is that you have to have a 7 volt peak to peak swing. If I have it biased at 5, I can probably get a 10 volt peak to peak swing because I can go to plus 10, which is 5 up. I can go to 0, which is 5 down. I get a 10 volt peak to swing, much better than design, right? So, all right. But you have some practical limitations. You can't really choose RC as anything. If this is 1 milliamp, I have to choose realistic resistors. So if it is if I want it to be exactly 5 and this is 1 milliamp, then RC should have been 5K. Can you get a 5K resistance? You can make one, but it's difficult. What is the closest of out of the box value for a resistance? 4.7K. Plus minus 5%. So if you put 4.7K, you get 5.3 here. That is 10 minus 4.7 volts. Good enough because you're only required to do plus minus 7. But there's still a wrinkle. We forgot to put in the RE here. The external resistance RE. Now of course once you put the external resistance RE, there's 1 milliamp flowing here. So the biasing picture slightly changes. But let's keep this relatively small so we can still use the same biasing. You can refine your answer later by putting a real resistance here. And now, so if I choose RC as say 4.7K, I'm even giving you the answer roughly. But let's say we choose it. And now we want RC over RE to be equal to how much? 25 or so, right? Again, you might want to choose a realistic value that you can get out of a box. Because if you build such circuits in real life and your component fails, you want to replace it with another one. Of course, these days we just throw the whole thing in the garbage. But if you did want to fix it, you'd want to replace this with a different one, you go to a box and take it out. You are not going to sit there and solder two things together to make sure they're whatever volts they are. So RC over RE is 25. If you put RC as 4.7, then RE comes out to be whatever it comes out to be. It'll probably come out in the neighborhood of around 400 ohms, which is still bigger than the internal resistance of this, which is 25 ohms. So all the design things seem to gel. You can go back and refine your design with these exact values, because once I put this RE in here, my swing over here will be limited. Because now I have here minus 0.7 volts. Here I have minus 0.7 volts. Right? If this is 0. Right? Well, maybe it's the same. Okay. So you can, as long as the RE is much smaller than that, you have yourself a circuit. So this, I think I've covered all the bases here. The only thing I haven't covered is CMRR. And I'll just give this formula without, I've already told you that the CMRR seems to be affected if I put a realistic resistance here. Instead of the 2 milliamps, if I had a realistic resistance REE, if I had a realistic resistance RE, then the common mode voltage would change the current in the circuit slightly. In fact, I had a formula there how much it would change. And I also showed you the common mode gain would be affected by these resistor values being different. And if you really, we won't prove it here, but if you want, this is the general formula for your common mode gain. The common mode gain is ACM. So AD we already have, and this is double-sided. Single-sided is half that. Or rather we say differential. Differential output, that means you are measuring the gain between these 2 points. We can also put the single-sided gain, VC1 only, which is half of that. So this is going to be equal to, we already said, what did we say it was? We had a formula for it. Approximately RC divided by 2 RE plus RE. And you can even ignore the RE, small r. Alright, so this is the formula for AD. And the common mode gain, ACM, happens to be, well, I didn't write unfortunately I didn't write the expression for this. It's something. But if you take the ratio of common mode gain to the difference mode gain, or difference mode gain to the common mode gain, this is called the CMRR. And this is equal to 2 GM REE divided by delta RC over RC. So, and GM of course GM is IC over dt. Should I read to the parameters of the thing? So this is the formula for this. So it's dependent on RE and it's dependent on RC. So now if I use perfect resistors, both RC is exactly equal, then delta RC is the difference between the two resistors. And so what will the difference be between the two resistors? So what should I get? If this is 0, what will be the common mode rejection ratio? CMR stands for common mode rejection ratio. Infinity. Is the common mode rejection ratio of infinity an excellent thing? Yes, it means that the differential gain is infinitely larger than the common mode gain. In other words, it means common mode gain is 0. So ideally we would like it to be CMRR to be infinity, and if we make sure that the two resistors in the collector are equal, then we will get this. You may measure something else because your collectors would be different. If you wish, and this is not asked for, well it's asked for, but I give you leniency to not do it, but if you are real seekers of knowledge, you will, is to check whether this formula really does predict. You could measure each one of your collector resistances with the help of a ohm meter, right? And check whether you can get your CMRR perspective. And then you can find out what delta RC is and what the ratio of delta RC over RC is. Either you can do it this way or you can just do it in a theoretical way, saying that let me assume that my resistors are the worst possible resistors I can get. So if these are the worst possible resistors I can get, and let's say they are 10K each, let's say they are 10K each, right? So what will delta RC be? Worst possible. What will be worst possible means that the difference between them should be the largest. And you took two 10Ks out of the box. When will the difference between them be the largest? Remember, each 10K resistor can vary from what to what? There's a 5% error. How much is 5% of 10K? Half K? Yes, I think so. 500 ohms, 0.5K. So we really, 10K means that it can be anywhere from 9.5K to 10.5K. And the other 10K resistor can be anywhere from 9.5K to 10.5K. It's our pick of the draw. Because that's all that we have guaranteed. So what is the worst condition? If we are terribly unlucky, what will we do? We will take the 10K resistor from one box and the 10.5K resistor from one box, 9.5K resistor from the other box because we are terribly unlucky. Right? And then you will find that your delta RC is 1K. So you can calculate the theoretical worst case that you can get with your resistors taken from your box, assuming whatever color band it has. If it has a 10% band, then the error will be more. So you can either give us the worst CMRR theoretically possible for this circuit, or you can measure the RCs and then give us the actual CMRR and compare whether it agrees with your circuit. I have no idea what to expect here. All right? And then you can talk to your TAs and say, tell them what you did. Either is accepted, even Grace, if you don't calculate that, that's fine. But as long as you understand it. But I solidly urge you to calculate it. It's great fun. All right? Any other questions? I think I've covered all the aspects of the lab. Yes?
The differential output gain, that's for the single, right?
No. Differential is double-sided. I think. Oh, I'm so sorry.
And it's negative, right?
Oh.
Yeah, that's true.
Probably if you say VC1 minus VC2. Of course, here we are only asking you for magnitudes. But correct, thank you. Yes, we forgot that the differential gain was the 2 would disappear. Yes, that was a single side. All right, any other questions? Okay, so you're on your own. It shouldn't be take too long. You don't have to do the piece-wise. Okay, and I think this will give you a head start on. I've really covered the entire lecture set 5 more or less. If you I did prove this, but that's the only thing really that needs to be proved now. Do it like this.
Yes,
All right, ladies and gentlemen, one thing I forgot. And you're required also to plot the bandwidth of your circuit. And what bandwidth means is, if you plot the gain, let's say this is the difference mode gain. So this is your difference mode gain 80. I'm not sure whether it asks you for the single-sided one or the double-sided one. So take its magnitude and change the applied frequency with your signal generator. And you will find, I think in this particular case, you will find that at very high frequencies, your gain will begin to drop. Around a megahertz or so. So your gain will remain constant at 20 log, say 25, if you have designed for a gain of 25. This is a logarithmic. This omega is also plotted on a log scale, generally speaking. And after some point, you will see that it will be done. And if you extend this, and you take this asymptote, this is the 3 dB point here, where the gain is 3 dB below here. And this is regarded as your bandwidth. Okay? So whatever this frequency range is the bandwidth, and that's the range over which your amplifier amplifies properly. It is not something we are going to learn in this class now. We're going to do something about bandwidth measurement later on in later chapters of our book. But here you're required only to measure it. So keep on increasing the gain until you find that the gain drops to 3 dB below. 3 dB below means it drops to 1/√2 of the initial gain. That is your bandwidth. You should maybe even make a plot of it, if you have time. I will leave this as optional. Okay? But it will be instructive to plot the bandwidth. And the reason it's optional, it won't be optional tomorrow. Remember this, guys, whoever is watching this, it won't be optional tomorrow because I've taken 45 minutes in this lecture. A lot of people ought to review this before they come. Right? So for them it's not optional. But for you guys, it will be instructive to plot the frequency response, but not compulsory. Thank you.